Ladies and gentlemen, I'd like to welcome you to the third week of our course on business process modeling and analysis. In this week, we will analyze process behavior. The week is organized as follows. We have 7 video clips altogether. 3 of them are bonus material, and I will say a few words in a minute about this bonus material. It's about process behavior and how to analyze process behavior. This in itself is a little bit on the formal side, a little bit on the theoretical side, but I try to explain the concepts as informally and as practical as I can. So in video 3.1, we define process behavior, what actually is the behavior of a business process. In the video 3.2, we look at structural soundness. So structural soundness is a prerequisite for soundness, which is the criterion that we will look at in this week. So video 3.3 looks at soundness and explains in an informal way what soundness is, how soundness can be applied to processes. In video 3.4, we look at simulating business processes before we start the bonus material. And the bonus material is still on the informal side, but again, a bit more formal than what we discussed earlier in this week. So 3.5 looks at an informal PetriNet primer, presents PetriNets, which is the formal foundation of behavioral analysis of processes. Explains PetriNets in a very informal, brief way also. Afterwards, in 3.6, we map bpmn process models to PetriNets. And in 3.7, we use PetriNets to check soundness, of the bpmn process model, so that we know that the bpmn process model is correct. In the bonus homeworks, you can own additional points. So it's not only that we have the bonus videos, but there will also be a bonus homework. And these go on top of the normal points, so you can own additional points so that you can improve your overall score that you achieve in this course. All right. In week 2, we looked at the syntax and also the semantics of modeling languages, in particular process modeling languages. And we defined syntax as, syntactic correctness makes sure that the elements of the model are organized in a way that matches the abstract syntax of the modeling language. And as an example, I have again this insurance claim process model that we discussed earlier already. So here we can check whether it's syntactically correct. So what do we need to check there? Well, we can take a look at the start event. The start event does not have any incoming edges. That would be syntactically incorrect. Start events do not have incoming flow edges, and the end events do not have any outgoing flow edges. Also, that is correct. We have a number of activities, and we have one gateway, and these are connected by sequence flow, and also the sequence flow, each sequence flow edge is connecting exactly 2 nodes, so that this process model, we can say, is syntactically correct. Even if we look at the role here, insurance company, we would say that is a syntactically correct process model expressed in the bpmn, so it complies to the abstract syntax of the bpmn. So how about semantics? Well, the semantics of a process model defines the meaning of syntactically correct process model. So we only need to have a meaning for a syntactically correct process model. The meaning is the behavior defined by the process model, which is the order of performed activities. So in this example, again, we see simple process, simple behavior. So we have an event that occurs, that is the claim receive event. That's the event that occurs in the beginning. All right, here we go. So that is the first event that occurs. And after that event occurs, register claim is executed, decide on claim coverage, and then there is a decision. Either we go the upper branch or we go the lower branch. Either of the two for each for each process instance, either the upper branch is taken or the lower branch is taken. And that's basically the semantics of this process model. We were discussing syntactical correctness, and now we turn to semantic correctness. Semantic correctness needs to ensure that a process behaves correctly and terminates properly. So, and this example shows that we can build process models that are syntactically correct, but they have they are semantically incorrect. They have a flaw that is, let's say, undesirable in process models. So we need to be able to detect these kinds of flaws, and this is exactly what we aim at in this week. All right. So semantic correctness ensures that a process behaves correctly and terminates properly. And to analyze semantic correctness, the process model needs to be checked for the absence of behavioral anomalies, we call it. So let's take a look at this process model. It's a variant of an order process in which first we analyze the order, or we receive the order, which is modeled as an activity here. Then we have concurrent branches, so we can package the products and ship or issue the shipment concurrently to sending the invoice and receiving the payment. Only after these two, there is the end split. Only after these two branches have completed, we have the synchronizing behavior of the end join here. And only if these two branches terminate, then the next activity can be started, which is checking the payment. In this process model, it's represented that the check payment has two possible outcomes. One is if the amount is invalid. So here we have the condition attached here, invalid amount. If the amount is invalid, we need to send an updated invoice to make sure that we receive the outstanding funds, or the remaining funds that have not been paid so far. All right, so let's assume we go the lower way. So the check payment activity resulted in invalid amount to be true. So the amount was not valid. We send an updated invoice, and then, we go to this and XOR join again. And what we do is we wait for receiving the payment. Assume the payment comes, we receive the payment. So we are at this position exactly, and we have completed the receive payment activity. So what happens in this process? Well, it should continue, but this is not what happens. Actually, this end join here waits for both incoming edges to be signaled, and here in this case only one incoming edge is signaled, namely the one from the receive payment activity. Therefore the process gets stuck. So it's a perfectly correct process model from a syntactic point of view, but it has this semantic error, semantic flaw, that it might get stuck. If the other branch would be chosen in the first, after the first check payment activity, then the process would terminate properly. But there are cases in which the process does not complete properly, and this is a semantic incorrectness that we should be able to detect. So this week we explained correct process behavior in an informal way. And as mentioned before, as bonus material, we also introduced Petri nets and a mapping from bpmn process models to Petri nets for a more formal investigation of correctness. Process behavior was specified so far also informally, so this activity has been executed and the other activity has been executed. Here we will make it a bit more precise. So the behavior of a process model can be characterized by the set of all execution sequences that are possible in this model. Therefore, we look at the traces of the process model resulting from events that occur and activities that are performed. So we look at activities that are performed and events that occur, and we build sequences of these events and activity, and thereby build traces, so to speak, traces of the process. And the resulting semantics is therefore called a trace semantic. So the trace are the steps that are taken during execution of the process. Okay, so in our example again, what are the traces? And each trace begins with claim received. So there's a trace claim received, register claim, decide on claim coverage, prepare letter of approval, and claim approved. That's one trace, one possible execution of the process. So we see that not all activities need to be present in all traces. Of course, we have the decision here. But there's another trace, and another trace starts like the first one. So receiving the claim, registering the claim, decide on claim coverage, but then prepare letter of rejection is executed and the claim is rejected. So there are two traces. This process model has exactly two traces. So this is shown here again. So traces in the example. Traces in the example are exactly the two traces we can see here. So the first one goes until approval, takes the upper branch, and the second one takes the lower branch. So there are exactly these two traces for this process model. In behavioral analysis, we abstract from the actual running state of an activity instance. So we said this activity happens and this activity is executed, this activity is executed. So we are not really interested in the running phase itself. And this is appropriate since we're interested in the logical ordering of the activities and not in the activity executions themselves. We're just interested in the behavioral analysis and looking for behavioral flaws. So what we actually do when we analyze the semantics using the trace semantics, an activity goes directly from the ready state to the terminated state. So there is a bypass, so to speak, of the running state, because an activity that is ready then in one step is terminated. We might even see that a bit more clear in this example that exhibits concurrency. So concurrency results in traces with an arbitrary ordering of concurrent activities. So in this abstract example, we have different traces. So each trace starts with the event I. So we label the start event I and the last event O. Reasons will be discussed in a minute, or later this week, I should say. So the first activity that happens here is A. So again, let's highlight that. That's the A. And then we have concurrency. And in concurrency, we learn that the execution paths are independent from each other. So B and D can be executed independently. So either B can start, or B can be executed, start can be executed. And then after B has been executed, C or D can be executed. And so let's assume D is executed, or D happens, I should say. Afterwards, E might happen or C might happen, and only if all of these five activities have occurred, have happened, we need to perform F. So F happens, and then the final event, or the output event happens. All right, so here we have not just two traces, we have a number of traces. And we have here, I've shown here the traces. The first one that is, sorry, I need to use the highlighter again. The first one is I. So I, A, D, So let's erase all that to make it a bit more clear. So we now investigate the first trace here. The first trace starts with I, then we have the A, then we have the B, then we have the D, then we have the C, then the E, finally the F and the O. So that's one way of executing this, so the first trace. In the second trace, we have a different ordering of the concurrent activities. So we first have B and C, and then D and E. In the last one, we also have a different ordering of the concurrent activities. We start with D and E, and then have B and C. So you see, if there's concurrency in a process model, we have a larger state space. More states can process can be in more states, and that makes it far more complex than just having sequential executions like we've seen in the first example. Right, in general, all traces are allowed in which IA is followed by any ordering of B, C, D, and E, where B occurs before C and D occurs before E, followed by F and the O. Okay, we now need to look at loops. And here in this example, we have a loop from, well, see it, after executing the first part of the process, we can step back to A, which is used as a join node. And here we can have loops of arbitrary lengths depending on the number of iteration. The number of iteration is not fixed, so there can be loops of arbitrary lengths. And one example is here, I would not discuss that, I think it's quite clear. So after the first iteration of these activities, I can jump back. So one loop iteration, one possible loop iteration trace is shown here. And also I did that once for 2 loop iteration, but you can of course expand that to any number of loop iterations, which increases the length of the trace, of course. All right, that concludes video clip 3.1, in which we introduced process behavior. We looked at syntactic correctness, but also semantic correctness, which means the behavior of a process model. We looked at an example where we have a behavioral anomaly, and we introduced traces as a means to characterize behavior.